Hello and welcome to this module. In this module we will talk about electricity supply system in osmosis. Specifically we will talk about wind and solar technologies. Here you can see where we are within the structure of our course. We have reached the third block of our capacity reserve technologies. Within the structure of our previously designed reference energy system, we will consider wind as a technology before transmission and distribution. For solar energy, we will consider residential PV panels with and without batteries. These will be behind transmission and distribution. However, we will also mention other uses of wind and solar energy. When we talk about wind power, there are certain key aspects which we should consider. Wind power is a renewable energy source. This implies that there are no emissions during operation. As wind itself is sometimes flowing and sometimes not, the production itself is also variable. This means we have seasonal, daily and hourly variations of the output of our wind power plants. In general, wind power plants do have moderately high investment costs, but low operation and management costs. As the wind is very site-specific, also the energy output of our wind power plants is very site-specific. For osmosis, we will talk about two different types of wind technologies: onshore wind and offshore wind. Here we can see the working principle of wind power plants. The kinetic energy of the wind itself is transferred to the wind turbine blades. The blades will turn the turbine shaft, which will spin a generator. The electricity generated in the generator will be transformed and distributed to the different end clients. When we are talking about onshore wind, we are talking about a very mature technology, meaning it is widely commercially available and utilized. Amongst others, there are already high cumulative capacities installed in North America, Europe and China. The overall performance of onshore wind power plants is highly dependent on the specific characteristics of each location. Commercially available turbines generate usually around 3 megawatts peak power, but much larger or smaller turbines are available. For osmosis, more turbines of the same group or technology type built at various locations with differing wind patterns means different capacity factors. In the table on the right, we can see some key characteristics for onshore wind technology. For example, capital costs of onshore wind is around 1,400 euros per kilowatt, or the average capacity factor of onshore wind power plants is around 23%. These are just some example values, and these values will differ for each model and each location. When considering offshore wind, we are again considering a very mature technology. However, this technology is mostly concentrated in Northern Europe, where the highest cumulative capacities are recorded. Whether onshore or offshore is more cost-effective in the long run is determined by the particular characteristics of the installation site and the wind turbines. For wind plants, no input technology is necessary, as we do not model the wind. We could, but since it is for free, it would not affect our cost optimization. However, in osmosis, the wind power efficiency and the profile have to be calibrated using the capacity factor and the availability factor. Remember, the capacity factor is for unplanned outages or capacity losses. As wind technology is very dependent from the wind behavior in the specific region, this will have a strong influence on the capacity factor. However, also other unplanned outages due to accidents or similar can influence the capacity factor. This means the capacity factor is time-slice specific. The availability factor is used for planned outages, for example for maintenance, and less dependent on the region. The availability factor is not time-slice specific. For example, we can schedule maintenance wherever we want. Here are some further aspects and tips for wind power. Wind power plants, and especially farms, tend to be further away from the end client. Therefore, we could model transmission for a more precise model. There are two options to do so. We can add transmission costs directly to the plant, or we can model the transmission line separately. Concerning the availability of wind power plants, especially the behavior during peak load time is important. We could model this very precisely, but this will also complicate our model a lot. It is always recommendable to check how the wind power plants behave, especially in comparison to the load. For example, when the load is peaking, the wind power plants should not be peaking all the time as well, because they are limited by the wind. The peak load and the wind power peak capacity may coincide at some points, but it is unrealistic that they coincide every time. Wind power plants are also not as firmly adding to the system capacity reserve as power plants that are more conventional.